Hi everyone, hope I'm audible. Okay, I think I'll proceed. If there are any audio issues, please let me know. So I'm not sure if you've attended any of my previous sessions. So this is one of the live interactive session that happens every week. Actually, two happens per week. This is one of those. You, you could probably choose to attend any one of these. And the objective of these sessions is to possibly rehash what you've read or gone through in the main NPTEL course, and to rehash what you've gone through in the main NPTEL course, and equip you with a live flavor of problem solving. So possibly this could help you in solving the current assignment problems. So how we do that is our instructions are to solve the previous year questions, previous year um, assignment questions, and equip you with enough knowledge to answer the current questions. Right? So today, for going into the questions, I'll talk a little bit about what was covered in the week 3 lectures. So what was the input and what you are expected to have learned out of it. And then we will go through the specifics of it. More specifically, there are 4 different types of tries that were taught, right? And these tries, how they built. And while building these, I'll also probably tell you a few techniques that will help you build it faster. Uh, although these are all shortcut techniques, these are not to be confused with the understanding. Once you understand, then you come to a conclusion that yes, some of these things you can just apply it blindly. Right? So this could help you speed up your problem solving. And as always, the sessions are recorded. Whether you attend or not, these sessions are recorded, and you can choose to go back and you can choose to visit the YouTube channel that I believe is published on the NPTEL administration page. Okay. Right. You can choose to go back to the NPTEL. Sorry, you know the link of the YouTube channel, and you can always take a look at it whenever you have time, right? So, at any point of time, if you have any questions, please feel free to just unmute your mic and speak, or you can also raise your hands, or you can put your questions down in the chat, right? Okay. Okay. So in week 3, you would have heard these terms. Sorry, packet classification and traffic management. Second. Just 1 second. Met everybody and okay. I think some people have joined recently. I'll just rehash it. So I believe in week 3, you would have learned about packet classification and traffic management. Correct. So let's just have a small overview of what packet classification means. And then let's look into some algorithms that help in packet classification. And these algorithms are trie-based. And in the previous week, you all would have understood and known what tries mean. And more specifically, these are the 4 tries that we'll be looking at today. First is hierarchical trie. We will look at its construction. And this is pretty straightforward. And the second is set pruning trie. Right. This is basically an optimization from here. So you optimize from here and you get to set pruning tries. Okay, you optimize from here and you get to set pruning tries. So basically, for the people who've joined recently, we're just discussing what went on in this previous week and what are the main things that we'll be covering today and the 10 questions that we'll be answering. Yes, we have hierarchical tries, set pruning tries, and then we also have just give me a moment. I'm facing some difficulty here. One second. Okay, sorry for that. Okay, and then we have grid tries, and this is also once again another optimization on the set pruning tries. And finally, we have field level tries. Okay. These are the 4 tries that we'll be looking at today, and we'll be answering questions based on these tries. And more importantly, all of these are connected with packet classification. So first, let's tackle this, and then let's go over to traffic management. All right. So what is this packet classification? So as usual, I take a bigger example, and then I'll bring it into perspective. So we have a network like this. These are all routers. We're dealing with routers. I think by now you should be familiar about. I think by now you all should be familiar with it. So this is you sitting here on your laptop, okay, and you're connected to the internet. Let's say this is the internet, and this is the server. So basically, every packet that you send to, let's say this is google.com. So every packet that you send gets routed over here like this, or here like this, or here like this, right? Okay, so that is the concept of packet routing, and we know how this happens. This happens based on the IP address, correct? But there is one more operation that these routers may need to do. And this possibly could go well beyond only routing. This could go well beyond routing, and we'll come to that. Maybe this router might want to drop some packets, or it might want to rate limit. Rate limit would mean do not send more than a particular number of packets per second from this particular endpoint. Okay, there are multiple such functionalities. Right? So these are all rules. We have some rules like this. So how do you implement these rules? So how do you implement these rules on top of this router? Right. So basically, when it comes to packet classification, you need to keep two things in mind. The first thing is flows. So what are flows? Let me clear this fundamental concept. I'll go from the scratch, just to aid people who might not be familiar with this concept of flows, because it might be confusing in the beginning. So a flow is nothing but a set of packets. This much is obvious. It's a set of packets. But what is the defining parameter that sets one flow apart from the other? These are the parameters: source IP, destination IP, source port, destination port, and then protocol. I hope by this time you're familiar with what these things mean. These are all header fields. This is L3 layer 3 network layer, and this is L4 transport layer, correct? And this is once again L3. This is a protocol field. So what are these? So basically, these 5 header fields, packet header fields, define a flow. Okay, Now you could ask why only these 5 header fields. So in most of the research literature, it is a well-used set of headers, and more specifically, these 5 fields can differentiate flows to a great extent. So it can take it with a pinch of salt that these 5 headers, right? These define a flow. Now, my question is, there is a source, let's say you, and you are communicating with google.com with, say, 121.2.3.4. Okay, this is google.com. So your source IP is 10.0.0.1. Okay, and you're sending packets. You're sending one packet, other packet, other packet, other packet. Okay. All of these packets, the source IP is going to be this, the destination IP is going to be this. And let us say you're using TCP. Okay, so the protocol field will also be 6. Okay, that signifies TCP. So in all of these packets, protocol is this, source IP is this, destination IP is this, and source port. Let us say this computer is using a particular source port of some random value, let's say 49654. Okay, this is the source port, and Google might have a source port of either 80 or 100, 80 or 443, based on whether it's HTTP or HTTPS. Let's say HTTP, and it's 80, so the destination port is 80. Now you're sending packets in this direction. So for all of these packets, this is true, this is true, this is true, this is true, this is true. Yes, correct. And what about the packets that return like this? For all the packets that return, these fields will be interchanged. Source IP will become destination IP, source port will become destination port, the protocol will remain the same. So essentially, what a flow means is it is a set of packets. See, these are all individual packets, but they're all part of this particular flow. That flow is defined by this 5 headers or 5 tuples. Okay. So this is the 5 tuple based flow that is defined in the network literature. All right. Next is, now that we know what a flow is, now these flows, they need to be classified, correct? So these flows need to be classified. So to classify, what is required? You need a set of rules, correct? Set of rules. And where would you implement the set of rules? Implemented in the router. Okay, so what we saw here, this router is going to be responsible for classifying all of these packets at a very high rate, right? So we all know the importance of uh, line speed packet classification. And what that means is you need to classify packets in an agile manner. You cannot spend too much time, and if you spend too much time, then the packet latency will be higher. So because of all these reasons, these algorithms are important, right? So now, how would a rule look like? Let us take an example. So let's say rule 1, rule source IP, destination IP, source port, destination port, protocol, and action. Okay. an action. So a table like this is what we use to represent such rules. Let's say rule number 1 is going to have 40, 20.20.20.1, 70.1. Okay, I'll go with the same example. Source IP is going to be 10.0.0.1. Destination IP is going to be 121.2.3.4. Source port is 49654. Destination IP is, sorry, destination port is 80. And then protocol is 6 and action. So what is the action? It is hello. So this is one rule. So every time these packets that I'm sending here go and hit this router, this is where the rule is present. What happens? It will match the source IP with this. Yes, matched. Destination IP, yes, matched. Source port, yes, matched. Destination port, yes, matched. Protocol, yes, matched. And then they're allowing it. Right. So this is one way you're classifying the packets, and you're in fact you're allowing these packets also. Now you could also have another set of rules. Let's say that 10.0.0.1, 121.2.3.4, and let me just say star and 80 and then 6. And for this also allow. Now this is confusing. You have rule number 1, which is working for this source port. Then you have another rule which has a star, which also has every other element or every other entry as the same, but the only difference is there's a star. The star basically denotes that it can be any value here. It need not be a particular value. It can be any value, right? But now you could see, okay, this value is repeated, this value is repeated. So now, if you start writing all such rules down, you will find a lot of repetitions. You will find a lot of stars. This is called a wildcard. Wildcard means anything goes there. You'll find a lot of such stars, and you'll have a lot of actions also. Maybe deny here, let's say. Deny anything else. You can allow only if the source port is this. So any such combinations are possible. So if you start writing this for every IP address that you have, it's going to be huge. It's going to be an explosion of numbers and entries, and routers. They don't have the memory capacity to store a lot. They don't have the processing, and they also don't have the processing capacity to process or parallelly look up multiple such entries. So this is where we have certain algorithms that we develop in order to optimize the way we represent these rules. All right. Okay. With that background, let us go. And yes, of course, you would have seen this in the lecture also. So these columns, right? These columns that you see, these are all called dimensions. So this is dimension 1, dimension 2, dimension 3, dimension 4, dimension 5. So this has it's a 5-dimension rule set. Okay. Okay. So by this definition, a classifier is a collection of rules. Okay. So this whole thing is a classifier, and it is nothing but a collection of rules. Right now, there are a lot more nuances here. You could possibly take a look at the video lecture where they talk about priority and the importance of priority. I'm not going into that right now. Now let's get directly into the hierarchical try. Put this down. I'll have to find a better solution for handling these questions. I'll find one for the next class. For this time, bear with me. Okay. Right. So there is a 5-dimensional rule set here. So we know what a dimension is. Okay, we know what a dimension is, and now all of these values are representable by binary language. So anything that is in computer science can be represented in binary numbers. So it's nothing but matching a set of binary numbers, right? So 10 is equal to 0, 0, 0, 0, 1, 0, 1, 0, yeah, 4. Yeah, so this is equal to 10. So basically, all of these things can be represented in binary. So there should not be any doubts there. If there are, please let me know. So this can also be represented in binary, 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 binary. So at the bare bones level, the router has to match certain combinations of zeros and ones. The router has to match combinations of zeros and ones. Okay. So this is what this is. So if you realize this, then we can just forget about whatever we spoke earlier and we can move on to the next algorithms, because sometimes when you talk about these algorithms, they might not be well connected with what you're reading, and you might lose context of why you're doing these classifications of what this algorithm, how is it used. As long as you realize that all of these are binary numbers, and you can always use any algorithm that works based on the patterns that you observe in binary numbers or anything for that matter. Okay. So now let us take a rule set. Simple example rules. The rule set is R1 is 0, 0 star, R2 is 1, 0 star, R3 is 1, 0 star, R4 is 1, 1 star, right? Let's say this is the source IP. Let's say this is the source port. Okay, let's look at destination port then. 0, 0 star and 0 star and 1, 0 star and 1, 1 star. So by this time, you might still have doubts about what is the 0, 0 star, what does the star mean. So it means any combination that starts with 2 zeros and ends in any way it wants. I don't care what comes after. The star means don't care. So anything that starts with 0, 0, match it. Then check destination port. Is it also starting with 0, 0? Yes. Then maybe allow it. Okay. If these matches, allow it. This matches, allow it. If this is the case, deny it. So this would be the action. Right? So we're just taking a very simpler example. This is how it is. So for example, here I told you, right, 10.0.0.1 can also be represented as 0, 0 star in certain contexts. Let's say this is also start 0, 0, and whatever comes after that, if I want to forward it, I can write this particular rule here. Okay. So essentially, this is just a toy. These are all toy examples for what actually happens in real routers, where you'll have bigger sequences. Probably you'll have, instead of 2 in the front, you'll have 8, 16, or 24, depending upon the network ID and everything, all that. Right. So this is source port also. This is just a number. So nothing to worry about here. So just keep this context in mind, and let us see how possibly data structure could be made so that these matchings can happen in a more efficient way. Okay. And we also know how to draw tries, right? We learned that in the previous classes as to how a try is built and what are the general rules. So you have a node. If you go left, it is 0. If you go right, it is 1. Okay, cool. As usual, let's take it. Let's take rule 1. What is there? There is 0, 0, star. You always start at the root node. Okay, and this root node is generally representing a star. Here there is no star, so always put the root node as star. So always put the root node as star. Okay. Now what is here? There is 0 and there is 0. Correct? And so basically you go a 0, you come to this node, then you go with a 0, and then you come to this node. Okay. And this is basically another star. So just to differentiate these end nodes, I'll shade them like this. Okay. So this is there. This is representing this. Now you have a choice. You can either go and represent this or this. But now we are talking about hierarchical tries. So by hierarchy, I mean this is the first hierarchy. I'll represent this first, and based on what is in the next hierarchy or the next level, I will represent the next set of entries. So R1 in the sense, the first entry, this is done. Now let us go with the second entry, which is 1, 0. Right? So this is 1, and I need to go with the 0. Okay. So far, so good. So this is 1 and 0. And now for R3, it is 1 and 0 and star. So which is pretty much the same thing. So 1 and 0, I've already represented it. It's okay. Let's keep calm for now because we still have a lot more levels to fill. For now, it is 1, 0, and there is a star. So what you see a star, shade it, and you keep it with you. Probably you'll get the intuition behind this once we start solving some more examples. And then R4, 1, 1 star. So I already have 1. I just need to draw one more 1, and then a star. That's it. Your first level, right? L1 is done, or rather D1 as I call it in lecture. So you've succeeded in representing this much. This much. You have represented this much. But the story does not end there. Now the point is, we need to represent the second hierarchy. Correct. So how do we do that? So for this, you just append the second hierarchy to the relevant shaded node. So which are all the shaded nodes? There is this one, and this one, right? So the relevant shaded nodes. So basically, for all of these shaded nodes, you are going to have another level of connection. Draw it. Okay. So for the second level of connection, I'll take black color and I will say. So for R1, if I take now R1, if I'm taking, I've already represented 0, 0, and it's going for another 0 another 0, and then a star. Okay. So when it comes to another 0, and a star, so there is 0, 0, and you need 2 more zeros, right? So here, when I said you can draw these different, I'm drawing in a different shape just to give context. So this is the second level, right? So the first level, you draw uh, the, the first level try. Right after you draw the first level try, you go ahead and you create links for the second level, because that is going to happen because you have more entries that you have to represent. So now with this in mind, we are looking at 0, 0. So there is 0, 0 behind this, and 0, 0 star is represented by this, correct? 0, 0 star is represented by this. Now if you come down, now we have the second level. So in the second level, I'll once again go for a 0, and then another 0, right? And then I'll finally have my rule 1. That's it. So now you have represented this rule. So if a packet matches 0, 0, 0, 0, the packet has 0, 0, 0, 0, then it will match with rule 1, and then the packet will be allowed. Simple enough. Now let's represent rule 2, R2. R2 starts with 1, 0. Do we have 1, 0 here? Yes, 1. And then we also have a 0 here, correct? 1, and then a 0, and a star. And then we have the next level ready for us to construct. It's ready right now. So now after this, what do we need? We need a 0, correct? Because there's a 0 here, and after a 0, it's a star, which means you've reached the final point. What will you put here? R2, because we're looking at this one, right? Correct? 1, 0, 0 star. So if you look at this, if it is 1, and if it is 0, and if it is another 0, then I want you to allow it, which is there. I have allowed it. In a sense, now in actuality, there will be one more action also associated with it called allow. But let's not look at that right now. Let's abstract the actions. So next is R3. So with R3, there is a small overlap. So where is the overlap? The overlap is in this part, right? We have this and we have this. So these are overlapping. And that we have represented already, correct? So it's 1, then a 0. So this part is going to be common for R3 as well. So R3 and R2 have something in common. So which is where we are saving some memory also. I'm not repeating these things. And yeah, so 1 and then a 0. But here what you see 1 and a 0. So from 1 and a 0, you need to represent, put one more 1. Okay. Sorry, this is just another dummy node and a 0. 0 is always towards the left. And finally, we have R3. Correct? So far so good. And then finally, R4. 1, 1 star. And then we need one more 1. And one more 1. And then R4. So that's it. So this is your hierarchical try. Okay. But now there are some questions that we will have to answer. One of those things is, let us say there is a packet with one zero one zero. Okay, let's take a different example. Just give me a moment. 0 0 0 1. Just give me a moment. Mm, 0 0 Okay, so I just wanted to show an example where backtracking happens, right? So if you're able to find an example with this, please let me know in the comments. Uh, if you can find an example for backtracking, right, in this particular place where a sequence of input sequence like 0 0 um, 1 0, let's say. So it takes 0 0, it does not find a 1, so it goes back. And okay, let's look at the backtracking with the second example. All right, so I'll come up with the motivating example, but if you can find one with this current parameters, please let me know. It'll be helpful for everybody, right? um, Now let's go towards a more complex example. Okay, um, consider this. 0 0 star 1 0 star. R2 is 0 0 star 1 1 star. R3 is 1 0 star 1 star. Okay. R4 is 0 star, 0 1 star, R5 is 0 star, 1 0 star, R6 is 0 star, 1 star, R7 is star, and then 0 0 star. Now this might look complicated, but once you get the hang of it, it's very simple. Right, now let's draw a hierarchical tree and let's do it ASAP. Simple. Rule 1, 0 0 starts. Okay, so 0 0 0 0 star, shaded this. Next you have, of course, first you look at the first dimension D1, then you represent that. Okay, 0 0 is done. Next is 1 0, so there is 1, and then there is 0, and then this is also and then this is also shaded. So this is done. So next is 0 star. So you have 0 and you have a star. You want me to see a star, you shade that also. Just shade it. That's all. You'll understand why later. So far we have represented 1, 2, 3, and 4, right? But we only have 3 shaded nodes because these two are common, right? Okay. And of course, this is also 0 star, 0 star. All of it is represented by this one, and then finally there is a star itself. And for a star, you shade the root node because this always represents star. It means it could mean anything. All right. So this is step 1 done. Your first tree is done. Level D1 is done. Right. So what do you do right after that? You draw these lines. Then you get ready for the next level, which I'm going to represent by right. We're done now. Now, what are you going to fill up here? Right. So for 0 0 star, 0 0 star, you have 1 1 0 star. So now it's going to be 1 1 and then 0. Right. So this is going to be rule 1. Done. Next is rule 2. 0 0 0 0 0, then 1 and then 1. So this itself becomes rule 2 because you see 0 0 1 1. Done. Rule 3. Rule 3 is 1 and then a 0, right? So 1 0, and from here you're going to see another 1 as a star, 1 and then a star. This is rule 3. And then you're going to go to rule 4, which is 0 star, which is right over here, and then you're going to go for 0 1 star, right? This is going to be a 0 and then a 1 and a star, which is rule 4. Rule 5 is, of course, we're coming to the same 0 star, and it's going to be a 1, correct? It's going to be a 1 and then a 0. This is R5. I think 1 and then a 0, right? R5. And then R6 is 0 star, but it is 0 star, but it's a 1 and a star. So 0 1 basically, correct? So this part becomes R6. And R7 is, you have a star and then you have 0, 0, 0, 0, and then a star, which is R7. Correct. So this is the second dimension, and so far it is yeah, and so far it is straightforward, right? But now you can do another optimization on this. And that is where the set pruning try comes in. Now for the set pruning try, let us take a previous example and let us just add one small extra node. All right. So let's take a look at the same example that was discussed in the class. So we have R1, R2, D1, D2. You will understand the rationale behind it once we're done. Star, star, and then 1, 0, star. This is a very simple example. So how do you represent D1 right now? So star, basically a star, and then you have 0, and then you have 0. Shade it, and right after that you have a star. Good. So what do you do next? You draw these lines. Okay. You draw these lines, and then you get ready for the next level. Okay. These are all protocols that you can follow so that you don't have to think much when you're doing these operations. So now you have drawn these lines and you've connected them to the appropriate nodes, right? Level 1 is done. Now let's go to level 2. So 0, I'm sorry, 0 here. So 0, 0 star will connect to 1, 1 star. This is 1, 1. So this is R1, correct? And what is R2? It goes through star, and the star is going to have 1 and then a 0. This is R2. So far we have created our set pruning try. Okay. Now comes the question. Okay, let there be an input sequence which says it is 0, 0, 1, 0. Okay, this is the input sequence. 0, 0, 1, 0. Now what happens to this input sequence? Let us take it. So you have 0 comes down here. You have another 0 comes down here, right? So far so good. Like this, it's coming down. It's matching. Okay, 0, 0 matches, well and good. And then it comes down here. It matches with 1 also. So 3 matches, well and good. But after here, it does not have a 0. So what will it do? It will backtrack all the way back, and then it will see, oh, there is a node here which I can traverse without any cost. In the sense, I don't have any rules, not 0, not 1. Anything goes. Because it did not find 0, 0, 1, 0 here, because there is only 1, there is no 0 over here, so it did not find the 0. So it backtracks all the way, and then it comes to this node where it finds a 1. So for 0 and a 0, it's taken care of, right? And finally, for 1 and a 0, this node is matched. So essentially, you are making the system do much more work, right? Although you're representing it in a very space efficient way, you are making the system do much more work. So what possibly can we do here? Now, as you said, if it, I mean, as I was previously saying, if I can add the 0 R2 over here, correct? If I can add the 0 R2 over here, the problem is solved, because the system, it matches 0 and a 0, the 1, and then it finds a 0 and R2, and this is matched and it allows, correct? So essentially what we have done here in a rudimentary way, okay, a rudimentary way is wherever we find a star, okay, this is where the shortcuts come in. Wherever you find a star, correct, you're going to go to all of the other nodes and you're going to add whatever value is here to this. That is it. Now you're going to repeat the same rule again and again and again, correct, for how many ever entries are there. For example, there is another rule 3 over here. You will add this to rule 3 also. So wherever you find a star over here, whatever is in the next level of this star, you're going to add it like this. Now we'll look at some more examples and this will become a bit more clearer. Okay, a bigger example would make this clear. So this way you can draw these tries, and what you have to understand is not to follow this blindly. It's you need to understand the rationale behind it, and once you understand the rationale behind it, you'll know that whenever there's a star, it means this could apply to any of the above, right? So you just need to expand it. So this is what is a set pruning try. So why are we using the set pruning try? Just to ensure that the packet matching algorithm does not have to backtrack. No backtrack here. Instead, it will find all the possibilities right here. It will find R2 right here. It doesn't have to go back and find it out somewhere else, right? But what is this coming at a cost of? Cost is space. This is coming at the cost of space. Why? Because I'm replicating this node over here. Correct? I'm basically replicating it. Right. Now we can take a look at another example where I told you the shortcut, right? But possibly you can understand it better. The more we do, the more you'll understand. So I believe so. See, the idea is you can watch the original lecture videos and you can understand what the instructor is trying to say and you can understand the rationale behind it. But in order to solve questions properly or faster, maybe some of these techniques could help you. Right? But do not follow these blindly, thinking without understanding the rationale behind it. Just a word of caution. Should probably find a better solution for this. Okay. Well, let us look at another example. The same example discussed in class, but now I will show you based on this rule, how you can easily draw the set bounding tribe. Okay. R5 0 0 star 1 0 star 1 0 star 1 1 star star 0 0 star 0 star 1 0 star 1 1 star 0 0 star. This is D1 and this is D2. Okay. Now let's start drawing. 0. Again, I'm starting with the first level. So 0 and then 0. And once you see a star, shade it over. Next 1 0. So 1 0 star, shade it. Again 1 0 star, it's repeating. So shade it. Keep it like that. 1 1 star, shade it. Okay. And then R5 is star itself. So shade. So we have all of these 4 shaded nodes. So what is the next step? Draw a line like this, like this, and this like this. Then you get ready for level 2. Right? Now that you're ready for level 2, this is D1. This is my next hierarchy, which is 2. What can you see for 0 and 0? There is 0 and 0. Okay. So 0 and 0. This is R1. Okay. And for 1 and 0, we have a 0, which is R2. Correct? This one. And two. For 1 and a 0, and for 1 and 0, we have R3. So 1 is here, 0 is here, again a 1, and then a 0, we get R3. Okay. So we get an R3 over. And for R4, it's 1 1 and 1 1. Right. This is R4. And finally for R5, it's 0 0 R5. So your second level is represented now. But now the question is, what are all the things that you will have to repeat? Correct. So now that your hierarchical try is done, so your hierarchical try is done, it's done. How do you modify this into a set point try? It's very, very simple. The moment you see a star, a lone star like this, you see what is to the right of it. You have a 0 0 star. All that you have to do is go and check for each and every one of these R4, R3, R2, R1. Does it have a 0 0 star extension? If it is not there, you're going to add it. Okay. Now let me show you. You have the star, right? Which means let me start with this one. 0, 0 is here, 0, 0 is here. And then does it have a 0, 0 star? Does it have a 0, 0 star? Yes, it is R1. So 0, 0, 0, 0 star is there. So no need to worry there. Correct? So let's take 1, 0. So there is 1 and there is 0. Okay. And right after this, does it have a 0, 0 star? There is a 0, but there is no one more 0 is not there. So you add a 0 and then star, you are going to add R5. Right. So we've added this to this. I mean, we didn't add this, we checked with this, we checked with this was not there, so we added. Next, we're going to check with this. Since both of these are the same, 1, 0 star, 1, 0 star, we don't have to add. Now let's see it again. 1 and a 0, and then 0, 0, R5. It's already there. We just added it because this is pretty much the same. Correct? So we checked, then we added. And finally, for R4, it is 1, 1 star. So 1, 1, and then after this, do we have a 0, 0? No, we don't have a 0, 0. We only have a 1, 1. So we just add a 0, dummy, then a 0, and then R5. So that's it. So this is pretty much your set coding trees tries. Okay. Now you need to repeat this process with every subset of the above. In the sense, in this case, there's only one star, which means this can also represent this, this can also represent this, this can also represent this, because star means anything. This can also represent this. Now let's look at a slightly more complex algorithm, complex example, where you'll have to look for subsets in the above also. You'll have to basically you'll have to look at the star as well, the star as well, the star as well, the star as well. All right. Let's take a look. 4, R5, R6, 7, 0 star, 0, 0 star, 1, 0 star, 0 star, star, star. D2 is 1, 1, 0 star, 1, 1 star, 1 star, 0, 1 star, 1, 0 star, 1 star, and 0, 0 star. Okay. We already drew the tree for this, but I would like to draw a better version of it so that I can show you how the same blind rule will apply for such a bigger example as well. Okay. Now quickly, I'm going to draw 0, 0, shade. I'm not explaining this because we've done this multiple times. So this is for 0, 0, correct? Then next is for 1, 0, shade. Okay. Next is 0 star, shade, done, done, and then finally star, shade. Next is what? Next, blindly just draw the next level dummy nodes. Okay. And what will be the structure of these dummy nodes? For 0, 0, we have 1, 1, 0. So let me draw from here 1, 1, 0. Right. This is done. This is R1. Okay, 0, 0, 1, 0. So 0, 0 is over here, and then 1, and then a 0. Right. Okay, sorry. 0, 0, and then 1, 1. Correct. 0, 0, 1, and then 1. So this becomes R2. Done. So next is 1, 0, and then you add a 1, and that becomes R3. Okay. Next is R4, which is 0 and a 0, 1. Okay. So from here you go with a 0, and then you go with a 1, and this becomes R4. Okay. And for R5, 0, correct, and then it's a star, and then 1 and a 0, correct. So I need to draw a 1 and then a 0, and this becomes R5. All right. And then for R6, this is 0 and then 1. So 0 and then 1. So this itself becomes R6 because 0 and 1, correct? And R7 is 0, 0. So far, so good. Now, apply the same concept or the same rule. Okay. So basically, right now, it's a hierarchical trie, correct? Now, let's make it into a set pruning trie. For that, what you have to do, you basically have to apply for all the stars that could represent any of the above. What I mean by that is the star here can represent this also. Sorry, can represent this also, can represent this also, because star means anything. Can this also, this also, this also, this also. So any of these followed by 0, 0 star should be accepted. So for that, what do? We go and check in all of these cases, in all of these prefixes, is there a way for 0, 0 star? If there is not, if there is no way, you need to add the way. That's it. Correct. Now let's look at R1. R1 0, 0, and then do you have 0, 0, 0, 0, 0, 0, and we don't have another 0 over here. So you add 0, and then another 0, and then this is one more replicated node, R7. Simple enough. What did you do? You basically just added this to this. That's it. And that's what has happened here in the try. Next, let me check for R2. 0, 0, 0, 0 is the same. Right? So 0, 0 and 0, 0 is the same. So we've already added it. So no need to add over here. Next, let's check R3. 1, 0. Does it have 0, 0 following it? Let's 1, 0. It does not have a 0 and a 0 here. So we add 0, and then we add another 0, and then now we are adding R7. So what we've added the same to R3, correct? And this is the addition. Okay. Next is R4, 0, 0, 0. Do we have 0? Yes, 0. And we don't have another 0, correct? So I'm just adding 0, 7. Okay. So which means I have added this to this also. And similarly, because all of these are the same, I've already added it to 0 star. So it will apply for here and here as well. I don't even have to check. So this is done. First level of set pruning additions are done. Additions are done. Right. Now going to the second level. So whatever we did here, right? What we did here, we saw if this can represent anything above. Because this is a star, this is able to represent every one of the components above. And that is why we added this node to every one of these components. Now let's repeat the same and check if there are any other entities which follow the same nomenclature. Okay. Let's take 0 star. Is 0 star contained in any of the above? 0 star could also represent 0 star could represent this, 0 star could represent this, because they're all the same. 0 star could also represent this, could also represent this, correct? So now we need to see, should we add 1 star to this, 1 star to this, 1 star to this, 1 star to this? That's it. So this is R6, right? Let's take a look. So 0, I'm looking at R1, 0, 0, and 1, right? Zero. Just give me a moment. Okay, I just didn't realize this. So do we have 0, 0, and 1? Yes, we have 0, and then we have a 0, and then we have a 0, and then we have a 0, then we have a 1. We already have represented this, so nothing more to add. Sorry for the delay. So basically, I'll repeat it again. you have a 0 and a star. So this can represent, this can also mean this can also mean this can also mean this can also mean this, meaning this can also be expanded into this. So which means I have to check for all of these. Do we have a representation for 1 0 at the end of this? Do we have 0 0 1? Yes, we have a 0 here, and then we have a 0 here, we have a 1 here. Okay, so that is done. R4, I mean, it is not R6, but it is accepted. So that's it. That's pretty much what we need. Okay. Now again 0 0. So this is also done. This is also done. Now this 0 1 accepted. Let's see, 0 1 accepted. Yes, 0 1. It's accepted. Done. Move on. Okay. Because 0 1 0 1 0 1. So it's all accepted. So no need to add R6 anywhere. Okay. R6 no need to add anywhere. Now let us check. Do we need to add 1 0 anywhere? Let's check. So this could either be added to here or here or here. Right? Let us check if 0 0 1 0 is there. 0 0 1 and then a 0. Correct? So 0 0 1 0 is not there. So now I've added 0 0 1 0. But here I'm adding the value R5. Done. R5. So we've added this to this. Next, let's check this one. So both these are the same. So it's already added here. We just added it, that is. Now, do we have to add a 1 0 to 0 1 0? Let us check. So 0, and then do we have 1? Then we have a 0. We already have R5 over there. So not to worry about it. That's it. So the check is done. So like this, recursively if you check for each and every one of these options. So now let's check. Does 0 1 have to be added to either this or this? We are going from bottom to top. Okay. So 0 0 0 1 0 0 0 but there is no 1. Okay. Now I'm adding 1 here. So what will I put? I'm putting R4. All right. So similarly, if you check, so R4 we have added already. So now we have checked this one, nothing else to do. Now if you take 1 0, nothing above this is contained, meaning 1 0 does not represent any of the above. You cannot combine these two because these things start with 0 0. It starts with 1 0. So there is no point of adding R3 anywhere else. And R2, do we have a need to add R2 anywhere? 2 3 4 5 0 0. We have to check for R1. So can we add, do we need to add 1 1 0 over there? Let's check. So 0 0, and then there is 1, and then there is 1, and we already have a node here called R2. That's perfectly there, and R1 also. Now we don't have to check. So basically we have added 1 2 3 4 5. So that's 1 2 3 4 5 extra nodes. So if you use this technique, you can just mechanically also do it. Although, I mean, this is useful for larger questions. In case you get a bigger question on an exam, you can definitely use this method, right? So now we've spoken about hierarchical tries. And set pruning tries. Right. Next is grid try. So what is a grid try? It is nothing. It is just the fact that, see, you already have an R7 here, but you're replicating it here. Why can't we? Why can't you put a pointer from here to here? Correct. Similarly, sorry, why can't you connect this and this? Right? It's possible. You can. And similarly, connect this, right? So which means you don't have to replicate all these nodes again and again at all the levels. Right? You don't have to replicate all of these again and again. That will just mean that for all of these 5, 2, 3, 4, 5, 1, 2, 3, 4, 5, you will have pointers going like this. I'm sorry, not to R7, to the corresponding nodes. Okay. So essentially that's what grid level tries mean. So with this context, let's go into some of the questions and let us quickly solve the questions. So during the lookup operation, which of the following try avoids backtracking? Now we have clearly seen that backtracking is a property of hierarchical try, correct? Backtracking is a property of hierarchical try. So which means that is not the answer. Set pruning tries, does it avoid backtracking? Yes, we saw it. Grid level tries, yes, because grid level tries is nothing but same set pruning tries, but it has got pointers to the corresponding node instead of replicating it. It saves space corresponding to set pruning tries. That's all. And then multi-level try, this is nothing but hierarchical try in a such sense. So the answer is B and C. Okay. Right. So let's look at question number 2. Let's look at question number 2, which is so which of the following try neither requires backtracking nor rule replication during the lookup operation? Um, so hierarchical try requires backtracking. So gone. Rule replication is required by set pruning tries. We are replicating certain rules, right? We're basically re-adding it. So it's gone. And hierarchical is the same as backtracking, is also gone. So grid of tries does not replicate rules, it gives pointer to the rules. That's all. Which means this is the answer. D is the answer. Right? Right. So question number 3 is so let's quickly go over question number 4. Right. So question number 3. Consider a 3-dimensional set pruning trie, which means 3 columns: D1, D2, D3, and the maximum field length for each field is 4, which means we'll have 1, 2, 3, 4. It's 4 bits, and there are 5 rules: R1, R2, R3, R5. Okay, all of these are only 4. This is what they're saying basically. How many times will rules need to be replicated? So if you watch the videos, you would know that uh, the number of rules to the power of the number of dimensions, which is d. So number of rules is equal to 5, and the number of dimensions equal to 3. This is 3 and this is 5. 5 is 3. 5 to the power 3 is 125. Right? So you may ask, what is the rationale behind this? So the rationale behind this is, you might have situations where pretty much all the possible rules need to be replicated at one point or the other. So in a way, this is like a theoretical upper bound, right? But this does not happen in practice. It's just an upper bound. Big O of. So basically, this is big O of, and I don't want to confuse you with algorithms here. Okay. So question number 4. So which of the packet classification schemes is the most efficient in terms of searching time? So is it hierarchical trie? Is it set pruning? Is it grid? Or is it both set pruning trie and grid of tries are equally efficient? The definitely hierarchical trie is not efficient because you have to backtrack, you have to go and come back, right? To come here, go, come here. So all these things are in a hierarchical trie. So that's gone. Set pruning trie, in terms of searching time, set pruning trie uh, is good. Let's keep it in our hands. Grid of tries, yes, it is nothing but same set pruning trie, but I'm not replicating nodes. So the only difference here is grid of tries uses less memory. That's all. But in terms of searching time, I'm not reducing the number of nodes. So in a way, both of these are equivalent. So that is, both set pruning trie and grid of tries are equally efficient. They're equally good. You can't differentiate. All right. But this is only in terms of searching time. If they say space efficiency, which is good, it is grid of tries, not set pruning trie. Just in case the question is different. Right. Now, question number 5. Okay. Now you must be very clear about. Is it the same thing that we did over previously? 0, 0, 0, 0. Okay, this is not the same one. Okay. So let's do this quickly. Right. So basically, consider the two-dimensional rule set. This is the two-dimensional rule set. To build a set pruning trie, each of the following rules are duplicated. So basically, you have to find out which are all the rules that are duplicated. So in a way, if you're used to doing it, you will you tend to know, you can guess to some extent what the answer is. But let's not do that. Let us quickly draw the corresponding tree. So once again, that's all 0, 0. Zero shade. So this is done. This is done. Next is 1, 0 shade is done. 1 shade, this is done, and 1 star shade is done. 0 star shade is done. Star shade. So pretty much all of these are going to have another level, right? So let us, as usual, draw the pointers. We have, say, over here like this. Let's have one over here, and let's have one over here. Let's have one over here, and let's have one over here, and this we keep it over here. That's for star. Correct. This is for star. Okay. At this point, what we're supposed to do? We're supposed to draw our dummy nodes. 3, 4, 5, 6. Okay. Now, let me just keep this to some extent over here. I need the table. Okay. Now for 0, 0. Okay. Now for 0, 0, it is 0, 0, 1. Correct. So now 0, 0, and I'm going to put 0, 0, 1. Okay. This is R1. So this is R1. This is 0, 0. Okay. R1 is done. So next I'll go for 0, 0, 0, 1 star. 0, 0, 0 is there, and then 1, and then this is R2. Right. Next is 1, 0, 1, 0. This is 1, 0, and 1, 0. This is R3. Okay. This is R4. 1, 1, 1, 0, 1. So 1, 1 is over here, and then 1, 0, 1. So for this, it's going to be 1, 0, 1, R4. Right? And then next is R5, which is 1, 0 star. So 1, 0, and oh, right, this is the second level, right? So this is 1, and after 1, you need to go to the next level because this is a shaded node. So here it becomes 0, and this is R5. So I hope you understood this point. I also wanted to make this point previously. For the second level, once you reach a shaded node, right, you can only append to the second level. So it's going to be 1, 0 star. So it's R5. And R6 is 0, 1, 0. There is 0, yes. And then I'm going to add a 1, and then a 0. This is R6. Okay. And then finally R7 is star. So basically R7 is 1 1. Right? So 1 and then 1 R7. Right? So your basic try is done. Now what do you have to do? You just need to follow the same rules that I was telling you the whole throughout the lecture. There's a star here. Now I have to see. I have to basically add 1 1 to every one of these above. Okay. So if you do it, it's R7. So I will be adding R7 at 0 0 1 1. Correct. So 0 0, and then after 0 0 there is no 1 1, so I'm going to add a 1 and then another 1. This is R7. Similarly, I'm going to add 0. So now that I've added this to this is also the same. So 1 0 1 1. Let's see, 1 and then a 0 and then a 1 and then a 1. So here R7, right? Because see, it's 1 0 1 1 1 0 1 1. Okay. Next, so I've added it to here. 1 1 1 1. Let's see, 1 1 1 and then 1. R7 is also done. So 1 1 1. Let's see, 1 and then 1. So this is 1, a 1 and then a 1. This is R7 again, right? And then finally, and then finally 0 1 1. Right? So 0 1 1. This is R7. So R7 is done, right? So now R7 is done. We have added this. We have accounted for the star. Let's take 0 star. So 0 star could also be could also represent R2 and R1. So what is here 1 0? We have to just check 0 0 1 0 0 0 0 1 and then a 0. So here it comes. So 0 and this is R6. That's it. Okay. Now I know because that it's not going to get added anywhere. So similarly, if you check in other places, you'll be finding that R6 only comes over here. Next is, let's try R5. Let us try R5. If you look at R5 1 star, so it could represent R4. It could also represent R3, correct? Now let's check if in this case it has to get added. So this has to get added here. Let's check. Is 1 0 0 star there? 1 0 0 star is not there. So now I'm going to put R5 over here. Okay, 1 0 0 star. Right. Next is 1 1 0 star. 1 1 and 0 1. 1 1 0, right? So 1 1 and 0. So if I see there is a 1 and a 1 and there is no 0, right? So I'm going to add a 0 and R5. All right. And similarly, let us see So we have basically added, we've done this, we've added 6, we've done 5. Let's check, is 1 star a reason to replicate? No, because none of the above can be contained in this. So this is not. And 1 0, no, once again, no. 0 0, yes, 0 0 star. So let's see if you can add 0 0 0 1 0 0 and then 0 1. So R2 is already here, so no need to add. Right. So basically, what are the nodes that we've added? It's R5, R6, and R7. So that is the answer. It's R5, R6, R7. So C, D, and E are the answers. Okay. So that's it. So once you, the whole idea of today's, what I wanted to impress upon in today's meeting was for you to understand that constructing a set pruning trie can also be done mechanically, and this will aid you in your examinations. And that is the point of these sessions, right? To make question solving easier for you. Right. So if you've seen the videos or the lectures, you would know that integrated, okay, which of the statements are true or false, right? So integrated service is one service that uses certain features to guarantee uh, flawless communication between point A to point B, because the internet is generally best effort. Best effort means you try to do your best, but if you can't, it's fine. Your connection might become slower, or might become uh, inefficient, right? But in this case, integrated services, you can watch the video for this. So basically, it uses a protocol called resource reservation protocol. So what this does is, if it has multiple routers from point A to point B, let's say this is point B, has to communicate, what it will do is it will set up a tunnel of sorts. It will reserve certain resources from this and create a path so that all the packets or flows goes through only this path. And for this, it needs to set up the connection. So basically, this becomes like a pipe that nobody can use. And resources are reserved for this particular pipe. So because of that, you can say D is correct, and it reserves resources on a per flow basis. Basically, that's what I meant. And it provides guaranteed quality of service. In the sense, guaranteed service. If I'm going to say you're going to get 10 Mbps, you're going to get 10 Mbps. It's not like people advertise that they're going to get 5 Mbps, but they're going to we only get 1 Mbps when we're actually trying the speed test, right? That's because many people are on it, so they cannot guarantee that speed. But in this case, integrated service can. All right. And question number 7. Let's do question number 7 in the end, because I've not touched upon it. If not in the end, I'll do it in the next week. So question number 9 is, so consider a two-dimensional hierarchical trie. What is the worst case search time for the two-dimensional hierarchical trie? This is also the same thing. So it is the depth, which is 5 to the power. We saw a similar question before. It's 5, and to the power of number of dimensions is 2, is 25. 25. That's it. I explained this previously. And which of the following statements are correct? So in order to guarantee the quality of service, all packets of a flow must follow the same route. Yes, without that, you have no control over where the packets are going. Then you cannot give a guaranteed service. So this is true. As soon as you read this, you know this is true. The packets that require guaranteed service will be served first before those that require best effort service. Yes, guaranteed service is one level above best effort, correct? So that means that it will be served before those that require best effort service, correct? To prevent packet loss, the first hop router may need to allocate a buffer for the source smaller than its burst size. Now, why should it allocate a buffer for a source smaller than its burst size? This doesn't make sense. The controlled load integrated service class is used for delay intolerant applications. Uh, integrated services, right? So we're talking about integrated services. It is used for delay tolerant applications. Sorry. It is used for delay intolerant applications only, but this doesn't make sense. So this is also wrong. And next is yeah, we have two questions. Probably all right. Question number 10 is slightly faster to solve it. So I'll just solve question number 10 here. So essentially what they're saying is, if you represent these rules, right, these port numbers, and if you want to bring them under a particular label, okay, because if you watch the video, you'll understand that such ranges are very difficult to match. So for that, what they do, they try to represent all of these with a label. Okay. So what will be the size of this label? What will be the number of bits required for this equivalence set? It is nothing but a label. A label. How many bits for it? Okay. Now let's take this one. Okay. You can take anything first, but let's take 21. Range 20 to 21. Okay. So whatever this matches, I'm going to give it a value of 1. Okay. And then next is, say, 53. So for 53, this is R3, this is R5, right? So for R5, I'm going to give it a value of 2. Next is equivalent of HTTP, which is R2. R2, HTTP is what? Port number 80. This is port number. This is 80. Okay. I'm giving it a number 3. This is equivalence ID. And then let's say R4, HTTPS. HTTPS is 443. So that's 4 I'm giving. Another ID, 4. And then finally I'm saying R6, which is anything greater than 1023, correct? This I'm getting the number of 5. And finally R1. So what is R1? It means star, which means everything that is not represented by this, I'll be giving it an ID of 6. So everything that is not represented by this could be, let's say, 0 to 19, and then 22 to 52, and then 54 to 79, 81 to 442, and then 44 to 1 to 1023, right? And this is basically, I'm excluding every number that I've written already above here. That's all. That's it. And that is it. So now we have these 6 IDs, right? So how many bits do you need? So this is a 000, 0, 0, let's say 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. Therefore, I need 3 bits. That's it. So the answer is 3 bits. Now for the final question. So this is something called field tries, correct? So I've not explained how to draw this try, and I think there is no time today. but I can give you an idea of how this is done. So for a field try, step 1, R1 to R6, okay, which is R1, R2, R3, R4, R5, R6. So you group it with respect to the rules. And now from this, if I am taking a star, which are all the rules that are applying R6, because this is the only one. Now from here, if I'm taking 1 star, what are all the rules that are applying? So there is R1, there is R2, and then there is R4, and then there is R6, because R6 will always be there. R1, R2, R4, and R6. All of these will be there. And now similarly for 0, 1 star, which is R3, R5, R6. Okay. And then for 0 star, which is R5, R6. And then finally for 1 star, you can say R4 and R6. So R6 is there everywhere. So intuitively, this first step is quite easy. Now for the second step, right, you need to go to the second level. So this follows a very similar rule in the sense that close your eyes and you can add the second level. So this is star ke baad you get 0, 1, right? 0, 1 star. So you're getting R6. Eyes closed, you can draw this. Okay. Next is 1, 1, 0, 0, 1, right? So for a transition of 0, 0, 1 star, correct? You're getting R1, correct? And then 1, 1, 0, 0 star. Again 1, 1, and then you're also getting 0, 0 star. So this is R2, which is basically for this. So you're basically writing that's all. And then for R3, it is 0, 1, and then 1, 1, correct? 1, 1 star, R3, and then R4 is 1, 1, 0. So 1, 1, 0 star. This is R4, and then 0, 1 star is R5. Okay. 0, 1 star is R5. So now you also have to consider one more thing. So now the template is drawn. They're all do we club things together? You see, 1, 1, 0, 1, 0, 0, 1 star can also be represented by R2 because this includes this. 0, 0 star could also mean 0, 0, 1 star, right? So that's why you add this one here. And similarly, if you notice here for R3, you can also add R5 because R3 is 0, 1 star and 1, 1 star. So this can also be 0, 1 star and this can also be 1, 1 star. So you add R5 and that's it. It's over. And next, finally, you basically connect whatever is there for star from all the other nodes, like this, like this, like this, and like this. Now, why are we doing it? Same concept that we learned before. Whatever is there for star, you're going to add it here, add it here, add it here, add it here, right? So in a similar way, you've added. But you also need to add 2 more pointers, and that is going to be here to here. And why is that? So 0, 1 and 1 star will give R5. Correct? 0, 1 and 1 star. You see this 0, 1 and 1 star should also be accepted, because if you go in the same method that we showed before, if you're going to see this 0 star also could include this. So are you finding 0, 1, 1 star? Yes. So you're adding that particular node to it. How you adding it? You're just um, putting a pointer from there to here. That's all. And similarly, from here, you can add a pointer over here. And this is for 1, 1, 1, 0. So which is 1, 1 and 1, 0. 1, 1 and 1, 0. So this is also accepted. So 1, 1 and then 1, 0 should also be accepted. That is why you're doing that. And with that, this level is over. And then finally, now it becomes a bit more easier for R6, correct? It is 10. So with the value of 10, you're putting R6, okay? And then for the value of 7, you're putting R1 over here, right? And then R2, you're putting 2, 6. And then R3, you're putting 3. And then R4, you're putting it for 9, correct? 4. And then R5, you're putting it for 1, 5. And then R6. Oh, R6 is already there, correct. Right. So we have added it. Correct. This is the template. Now, there is one more aspect to also see here. You have to understand that 0, 1, 1, 1, 0, 1, 1, 1, and 3 could also be in R5. See, 0, 1, 1, 1, 3, 0, 0 star, 1 star, and 1, 5. So this 3 is included in 1, 5. We should also put R5 here. And that's it. Now, where all will you put the pointers? First thing is it 1, 1 star, 0, 0, 1 star, and 7 is going to give R1. Clear. But 1, 1 star, 0, 0 star is also includes this 0, 0, 1 star. This can also say it as 0, 0, 1 star. So this should also go to R2, which is why I'm adding a pointer from here to here. And I'm going to say 2, 6 should go over there. Done. And the next is, if you look at R3 here, it's slightly different because there is an overlap. So if you look at R3 and R5, correct? R3 and R5, 3 is included in R5, which means 0, 1, 1, 0, 0, 1, 1, 1 should go to 3. 0, 1, 1, 1 is going to 3. Good. Correct. But 0, 1, 1, 1 should also go to 5. It is going. But to be more specific, if it is anything other than 3, it should go here. That is why it is 1, 2 union 4, 5, which means, I mean, you have to add these kind of brackets, sorry. So this means that it is a more specific rule. If it is 3, definitely it goes to R3 or R5, we don't know. But if it is anything other than 3, it needs to go to R5. And that's it. It's done. And the final level is straightforward. This is R6, 12. This is R1, 9, 12. This is 15 R2, and this is R3, just 7, because see, these are all values from here. 7, and this is R5, which is 10, and this is 15 R4. But the only place where there's a difference is between R3 and R5. So R3 and R5. So it could either be 3 or 1,5. But if it is anything, if it is 1,5, it should is if it is 1, if it is following this line, then it'll encounter a 10. So based on the 10, it has to go to R5. Sorry, this is R5. It has to go to R5. So I know I went a bit fast on this one. So essentially, this is, you can do this procedurally also if you follow the method that I showed before, where you take the star, then you expand it across the other ones on top. You take the next element and check if it can be represented by the elements on top. And if it is, then check if it can be added. If it can be added, then well and good, draw the try. If not, then move on. Keep doing this again and again for all the combinations, and then you'll see that you're done with the try. That's it. So the session is done. If you have any questions, you can ask me. Otherwise, you can leave the call. Thank you. I'll be here for 5 more minutes. All right. I'll be stopping the recording. Okay. Thank you.